Okay, today we will talking about the plane problem. The plane problem that is for this course we will limit to just only the constant strain triangle. Okay, we will limit to just constant strain triangular elements. Triangular is mean that the element is the triangular shape with just only 3 nodes. Okay, so for another type, okay, for another type, is it the procedure is the same. If you understand the constant strain triangular element, the basics of this type, okay. So for another type, is the same procedure, but you will see that the element size is bigger than this. To the For that case, we will not focus in detail on that. Before we talking about the constant strain triangular element, we have to review a little bit on uh, engineering and in mechanics of material, that is talking about the stress and strain relationship. Okay, so as we know that if we would like to analysis and design of structure, okay, all deformable body mechanics problem fall into one of two categories that we have to concern. That is the strength. We have to focus on the strength of the material, and we have to concern about of the stiffness of its material. Okay, a structure must be strong enough. That is mean that it must satisfy prescribed strength criteria. Strong enough, so it means that it's not broken. It's not broken, or it's not breaking out. Okay, and also it should be stiff enough. Stiff enough. It means that its deformation must be within acceptable limit. Okay, for example, if you have the ruler, if you imagine like the ruler, okay, so you may bend it, and it's not broken. Okay, it means that it is strong. Its strength can resist your bending moment, that you apply bending moment, you apply moment. But if you use it like a beam, okay, it may be not stiff enough because it's deflection. It has large deflection. So if you would like to use that ruler to support the some load, okay, it may be not suitable for that. Okay, so in view of analysis and design, we were talking about to these two category, strength and stiffness. Okay, and we will when we solve the structural problem or mechanics problem, we have to focus on three fundamental types of equation. Okay, that is the first one. The first one, it is the equilibrium, the set of equilibrium equation. Okay, that is you you have familiar with it. Okay, that is summation fx equal to 0, right? Summation fy equal to 0, and summation moment equal to 0. This is the set of equilibrium equation. If it's just only the plane problem, for the plane problem, we will focus on just only three equations. It is summation fx, summation fy, and summation moment. Okay, but if it is in space, the problem is in space, okay, or in the three-dimensional, the equilibrium equation is changed to be six equation. It is summation fx equal to 0, summation fy equal to 0, summation fc equal to 0, and also summation mx equal to 0, summation my equal to 0, and summation moment in c direction equal to 0 also. Okay, so for three-dimensional, we have six equations. Okay, this is just for the case that If the problem that can solve by using such a set of equilibrium equation only, if the problem can use the equilibrium equation to solve it only, we call that problem is statically determinate structure. Okay, if the structural system that we would like to solve is can solve by using the set of equilibrium equation only, we call it like the statically determinate structure. Okay, but as you have learned in mechanics of material and in structural analysis, you see that normally the most of structure that we analyze is not statically determinate. Okay, it may have the additional and unknown additional redundancies to increase the overall stability of the structure. So the state of equilibrium equation is not enough to solve it. Okay, you have to apply the compatibility condition. You have to apply the compatibility condition that is talking about the geometric deformation, okay, or the boundary condition of the support. Okay, you have to know it, and then you have to use the constitutive relation. Okay, that is the material behavior. That is that for the case of the linearly elastic material, we obtain the Hooke's law to solve it. Okay, so we have to know the material relationship that's related with the stress and strain, and we can change it to be the load and displacement. Okay, so the constitutive relation is maybe right in form of stress strain relation, or you may use the load displacement relation also. That actually it is the same. It's come from the stress strain relation. Okay, so to solve the problem that have the redundancies, that is the indeterminate structure, okay, you require to set up the additional equation, not only the equilibrium equation, that we may call is the compatibility condition. Okay, compatibility condition is maybe just the deformation like the support. Okay, like you have learned in by force method. You see that, for example, you have the continuous beam like this, subject to the distributed one. Okay, you have to change the this structure to be two of them. That is, if I reduce the support, if I remove the support, the middle support, okay, you see that it's become two statically determinate problem. That is, the first one is the simple beam subject to just only distributed load. You will find that you can find the deflection at the support that you remove. We may call it this delta 1, right? Okay, and after you remove it, is have to plus with the beam that is subject to the load. That is, we change the reaction force of this support to be the redundant force R1. Okay, and according to this is the same, is half the deflection delta 2. Okay, I will show you that from this structure actually has 4 unknown, right? It has 4 unknown. Okay, but you have just only 3 equations. You have only 3 equations of equilibrium. 3 equations of equilibrium is like this: summation fx, summation fy, summation moment. But you have 4. Okay, you have 4 unknown. So how to solve this 4 unknown? We have the additional equation. We have to know what is the additional equation. So from the force method, you will see that according to this step, okay, the set of equilibrium equation we already used it, and we have 3 equation, right? That's okay. It's already checked. So after that, we will move on because we would like to have the additional one. So we use the compatibility condition. We use the compatibility condition. That is what? That is the boundary condition at this support. So what does it mean? It means that you will have the equation that is delta is equal to delta 1 plus delta 2. And it should be 0, right? Because it is the boundary condition. Okay? So according to this step, you will see that you have the additional equation. You have the additional equation to solve the 4th unknown. Okay? But the additional equation that you obtain is obtained from the boundary condition, or in general case, it's maybe called the compatibility condition. Actually, it's maybe for the case that the structure is maybe not the support. So for example, if you have the clip problem like this, you have the beam, the cross beam over here. So you will see that at this point, the deflection of the beam number 1 and beam number 2 should be equivalent. So we may set up this compatibility condition again also, but delta is not equal to 0 because it is not the support. Okay. So in general, we will not call it like the boundary condition only. It is the compatibility condition, that is the geometric relation. Okay. So, but for this case, how can we solve for delta 1 and delta 2? Okay. To obtain delta 1 and delta 2, we have to use the constitutive relation. Constitutive relation. For example, you know that delta 1. Okay. You use constitutive relation, that is a stress-strain relation, that is the linear. For this case, after if you review in mechanics of material, you know that for the beam, simple beam subject to the uniform distributed load, the deflection at the midspan, for this case, we may assume that the continuous beam has a span length that has an equivalent span length. So delta 1 is the deflection at midspan. Deflection of the simple beam subject to distributed load, uniform distributed load at midspan is equal to what? Okay. So we know this relationship, but actually before we derive this relationship, we have to use the stress-strain relation before. Okay. After you use the double integration, you will obtain this equation. So you will see that for this relationship, so what does it mean? It means that you have the relationship between what? Between delta, that is the displacement, and the load, that is W. Okay. So another value you will see that it is 5,384 EI and L power 4, they are constant. They are constant for the particular problem. So what does it mean? So we can write it in terms of the force and displacement relationship. So that's why we use the constitutive relation. So for statically indeterminate structure, we have to use 3 sets of this equation. Okay. So this is just a little bit review for the mechanics of material and structural analysis. Okay. And then if we come back to the mechanics of material, we already know that the normal stress is defined by the unit, the force per unit area. Okay, the force that is perpendicular to the plane, to the plane cross section. And if we are finding the force per unit area, we will obtain the normal stress. Okay, we call this normal stress, that is the perpendicular to the area that we focus on. Okay, so according to this, if we talking about the stress along the y plane, for this case, this is we call the y plane because it is the plane that is perpendicular to the y axis. We call the y plane. Okay, for the case that the plane perpendicular to the x-axis, we call this is the x-plane. Okay, so if we talking about this plane, okay, and we have the force that is perpendicular to this plane, and we find the force per unit area of x-plane, we will have sigma x, that is the normal force along the x-axis, along the x-plane. Okay, along the x-plane. And if we talking about the plane that is perpendicular to c-axis, okay, in the same manner we will obtain sigma c also. Okay, to this point, do you have any question? Same as y, you have sigma y. Okay, now you know sigma x, sigma y, sigma c already, right? Okay, that is if we talking about the plane that is cut perpendicular to x-axis, y-axis, and c-axis. In the same manner, if we talking about the shear stress, the shear stress is what? Is the force per unit area also, but the force is parallel to the direction of force is parallel to the plane. Okay, the tangential or in plane component. Okay, so the force is in tangential direction of the plane. Okay, or it is parallel to the plane. Okay, we call it the shear stress. So for this, if we focus on the x-plane first, if we focus on the x-plane, come back to the x-plane again. If we focus on the x-plane like this, okay, so for the x-plane, we have the normal stress, sigma x, right? Okay, so if we set up the positive sign convention, x, y, c, follow the right hand rule, this is the positive one. So on the x-plane, this is the x-plane. Okay, we have the normal force sigma x, and it may have the shear force. Okay, it may have the shear force also. It may have the shear force. For this case, it may be tau x y. Why we call this tau x y? Because it is the stress on plane x. Okay, and it is on the direction of y. So we call tau x y. The first subscript represent the plane. The second subscript represent the direction. Okay. If we talking about another components, that is the shear force on plane x, but it is in direction of c direction, so we call tau x c. Okay, it is tau x c, tau x c. That is what? That is the shear force on x plane, but it is in components that is in c direction. Okay, you understand? You understand? So according to this, just a little bit. If we talking about the another plane, we talking about x plane already. Now we will move to y plane and z plane. So for y plane is like this. This is perpendicular to y, right? Okay. For y plane, so what does it be? It should have the normal stress first. The normal stress is what? It is sigma y, right? Okay, normal stress is sigma y. Normal stress is the force per unit area, while that force is perpendicular to that area. Okay, so we should have another component, that is this. This represent what? It should be tau what? What's plane that we consider? Now we consider y plane. It should be tau y, right? But its direction is along x direction, so we call tau y x. Okay. So next, we have another component. This is the shear force also, because it is perpendicular to the plane that we consider. We consider plane y, so it's become tau y. Okay, it's become tau y. And tau y in c direction, so it is tau y c. Okay. If we talking about the c plane, for the c plane, that is maybe this plane. So for c plane, we also have sigma c. That is the normal stress. Okay. And if we talking about the shear stress, it may have tau. For this case, we talking about the stress on plane C. So we call tau C x, okay, because it is in x direction. And we have another one that is tau what? On plane C, we call tau C also. But it's in y direction, we call tau cy. Okay. So if we consider the stress at a point that is maybe occur, actually it is a point, but we may consider the stress in different point of view. Okay, in different point of view. So for the stress at the point that is maybe composed of at least 6 components, according to the stress in x plane first. If we focus on the stress on x plane first, okay, for the stress on x plane, we found that it has 3 components, right? It is sigma x, tau xy, and tau xc. Okay. So for these 3 components, x is along x direction, this is along y direction, this is along c direction. Okay. But these are scalar quantity. But if we write it in terms of stress vector, change it to be stress vector, or we may call it is like the traction. Okay, so we have the stress vector on plane x. Okay, stress vector on plane x can be write in the vector form like this. It is equal to sigma x I plus tau xy j plus tau xck. Okay, you understand? So according to this, so that means that at the plane x, the stress vector is maybe like this. Okay, it's maybe not, it has 3 components. So if you understand, it has 3 components. Okay, so the direction is maybe not along just only x, y, or z. So it is in space. In the same manner of y, of plane y. So we have sigma py also. But sigma py is equal to what? Is equal to tau yx I plus sigma yj plus tau yck. Okay. And if we draw the traction along the plane y, it may be like this. It is sigma py. Okay. And if we're talking about the stress on plane C, on plane C. Actually, this is a point, okay? On plane C, it is the same. It has sigma PC. Sorry. Sigma PC equal to what? It's equal to tau Cxi plus tau Cyj plus sigma Ck. Okay, so according to this, we also have the stress vector. It's maybe like this. That is sigma P what? PC. Okay. So according to this three vector, but actually it is the stress at a point. So that means if I draw, it's come from the same point. It's maybe sigma Py, sigma Px, and also sigma Pc. Actually, it's at point. It's maybe at point P. Okay, so if we combine these vector together again, so we obtain sigma P. Okay. Okay. And the sigma P is straight at the point. This is maybe convenient, more convenient to represent it into the stress component in each plane, So that's why we have to define the stress tensor. What is the stress tensor? The stress tensor represents the state of stress in three-dimensional. It represents stress of stress in three-dimensional. Okay, that is represent what? It represents sigma px, sigma py, and sigma pc. Okay, so before we talking about that, we have to focus on the stress notation. In mechanics of material, and in advanced mechanics of material, we have three equivalent notation that used for orthogonal coordinate system. Okay, we normally, it is very important. It's important because it's the stress notation when you write the paper, when you write the report or something, you have to use the notation in this t-type, only, and you have to select it. This is the first type and second type and third type. Okay, so for previous slide, I using the second notation. You see that I represent sigma x, sigma y, sigma c like a normal stress, but I represent tau xy, tau xc, and tau yc as the shear force. Sorry, as the shear stress. But for another one, for another textbook, it may be used the first notation. For the first notation, it represents sigma x, sigma yy, sigma cc like a normal stress. The first index, the first subscript represent the plane. The second subscript, sigma ij. Okay. The first subscript represent plane. The second subscript represent direction. Okay. So for another notation, it may be used sigma x, sigma y, sigma cc. And it's not used tau anymore. It's used sigma again, and it's represented by sigma xy, sigma yx, sigma xc, sigma yc, and so on by this table. And another type of notation is in number. It is used in index number. It's normally used in the text of continuum mechanics. Continuum mechanics. Or it's maybe talking about the tensor analysis. If we're talking about tensor analysis, we normally use it's like the index because it's easy to count. It's easy to count like sigma ij. And I is 1, 2, 3. And also j is 1, 2, 3. Okay. Okay. So according to this, we will not mention it in depth because it's just only the notation. If you would like to know, you may consult with the textbook of continuum mechanics. That is write the constitutive relation in index notation. Index notation is maybe used for it is convenient to write the equation in short. Write the equation in short because it is in index. But for the student that is not familiar with the index or mathematics, you may confuse. Okay, so I will not mention it too much. Okay, right now I would like you to mention that we have three types of stress notation, and because I use a different text, so you will see that you may find that the stress tensor or the stress notation is maybe different in the form, but it's not different in this T type. Okay, so come back to the state of stress. If we come back to state of stress, we will see that if we focus on the stress along the x plane, we have three components. This normal component, and this is shear component. These are shear components, and we will have the stress component over here. Okay, that is the first row represent sigma px. Okay, and if we're talking about the y plane, you will see the stress component sigma yy, sigma yx, and sigma yc. Okay, that is the second row of the stress tensor. Okay, that is sigma py, represent sigma py. And if we're talking about the stress component along the C plane, we have three components also, and it's represent sigma pc. Okay, so at this moment, do you understand for the stress tensor or the stress component? That's normally we call it like the state of stress. State of stress in Thai we call it สถานะ stress. In Thai we call it สถานะ stress. Actually it is the stress at a point. Okay, so I will for this you will see that actually the state of stress or the stress tensor, we have 9 components because it is 3x3 matrix. Or it is if we talking about the tensor, it is a second order tensor, second order Cartesian tensor. Okay, and we normally familiar with the metric. So it's like a matrix. Second order tensor is like a matrix. Okay, we will not mention on the tensor because it's maybe out of our scope. Okay, so for the stress tensor, actually it's like the two-dimensional array, two-dimensional matrix. That is 3 by 3. 3 by 3, you will see that it should have 9 components. But if we consider the equilibrium condition, and we taking the moment at the center of the element, we will find that the summation moment along each plane is equivalent. Okay, it should be 0. So sigma 1 2 or sigma xy and sigma yx or sigma 2 1, it should be equal. That is the symmetric condition. It is a symmetry condition. For the symmetry condition, so it means that for the stress tensor, that's normally it should have 9 components. We may write it in the general form, that is sigma xy, sigma yx are equivalent. Okay, so this is a symmetry case of the stress tensor. Okay, actually I can derive it for you for the plane problem. Normally I think you have learned this topic before in mechanics of material, but you focus just only on plane problem. If we focus just only on plane problem, so the notation for plane problem, I think you may familiar with this. This is the notation for plane problem. This is positive sign convention. I will use the first notation in order to easy to use. I like the first notation because it's easy. It has the second index. It is sigma xx, right? You remember? This is sigma xx. Okay, so this is sigma xy. Okay, this is sigma yy. Okay, so in the same manner, if we consider this plane, it is sigma yy also. It is sigma xx, and it is sigma xy. Okay, so actually when we talking about the equilibrium condition, if we focus on the small elements, that it should be dx. Okay, so this is sigma xx, this is sigma xy, this is sigma yy, right? And this should be dy. So if we consider the equilibrium condition for moment, okay, equilibrium condition for moment. So if I taking moment at this point, so what happened? It has sigma xy, right, times dx. Okay, okay, but because the stress should be changed to the force first, it have to change the stress vector to the force first, that it should be multiplied with the block. The block, that is what? The area. This is the x, this is the y, this is the c. So for the area of the x axis, okay, this is plane x. The area is dy dc, right? Okay. and we multiply with the x. Okay, and also if we taking the moment along this point, so we have another one for sigma xy, the rotation is about this. Okay, but for sigma x yx, I have to write it in different first. So it should be sigma yx. It should be sigma yx also. So in the same manner, we have sigma yx. So for the plane y, the area is what? The area is dx dc, right? But the moment arm is what? Moment arm is dy. Moment arm is dy. And the rotation is about this. So it should be this term. After this, I checking the summation moment. If I set up this is as a point O, summation MO, what happened? It's become sigma xy. If we use this is positive one. Sigma xy dy dc dx minus sigma yx dx dc dy. So what do you think? This term is the same, right? So what happened? And this equation is in equilibrium. It should be 0, right? So what happened? It's become sigma xy minus sigma yx multiplied with dx dy dc, right? Equal to 0. But dx dy dc is not equal to 0. So what does it mean? It means that sigma xy minus sigma yx is equal to 0. So what does it mean? It means that sigma xy is equal to sigma yx. That is the symmetry condition in the same manner with another components. Okay, so for the stress tensor, is symmetry. Okay, so when we write the stress tensor, it is a symmetry case. So for today, I think we will just focus on the stress tensor first, and because we have to overview to the theory of elasticity before, because it is important to move on the plane problem. So according to this, I will just for example, to represent the stress tensor or stress notation. So at this point, do you have any question? No question, right? Or no understand everything at all? Okay, let me focus on the basic one, the tensile test of the bar. For the tensile test of the bar, if we consider the general bar, okay, subject to the load P, when we cut off the cross section over here, so what happened? What happened? So if we draw the free body diagram of this section, This is the normal force. That is the internal force inside of the bar. This is the actual force. Okay. Okay. So what is the stress? This is the area of the bar. Okay. So the stress is what? The stress had to be determined from the normal force, that is N over A, right? But from equilibrium, we know that P equal to N. Okay. So we have to set up the coordinate system first. For the coordinate system, it is X, it is Y, it is Z, right? So what do you think? For the case of uniaxial load, this is the uniaxial load. That is the case that the bar subject to the tensile test, subject to tensile test. This is uniaxial load. How many components of the stress at this point, if we consider the point, the stress at a point, this point, if we consider this point, this may be point O, okay? Sorry. If we consider this point, this may be represented by point O. And if we consider the small element of point O at this section, and that we already cut off, and we consider it's in three-dimensional, it's become the cubic shape like this also. Okay, this is a small element, but we zoom it. Okay, we consider the point O. This is a point O. Okay, so according to this, what do you think? Sigma x is equal to what? If we consider plane X first, it has only one force. It has only one force. So it means that sigma x equal to 0, right? And then sigma xy is equal to 0 also. And sigma xc equal to 0 also, right? Okay. If we consider the C plane is the same. Sigma cc equal to 0. Sigma cx equal to sigma cy equal to 0 also. But if we consider this component, we have sigma yy. Sigma yy is equal to what? For this case, is equal to N over A, that is P over A, right? Okay, is the applied load. But sigma yx and sigma yx and sigma yc are 0, right? So can you rate the state of stress? Of this condition? Stress of the uniaxial bar. What is it? Stress of the uniaxial bar is what? Sigma x 0, right? Sigma xy 0. And then sigma yx 0 also. But this you have just only sigma yy. And in this case, we have just only one component. You understand? Okay. But if we're not talking about the uniaxial stress anymore, we're not talking about your uniaxial stress problem. If we're talking about the beam problem instead, the beam subject to distributed load. If we consider the section at midspan, okay, if we consider the section at midspan, and we focus on this point, at this point, at the bottom surface of the beam, it's not on the top surface. If we focus on the bottom surface, at the bottom surface is subject to tension, right? And we study from structural analysis and mechanics of material. So if we focus on this, what is the state of stress at this point? Okay. So at this point, what it is? What is it? At this point, we have, if we set up the axis first, x, y, z, right? So at this point, we should have sigma x, right? Sigma x, that is equal to what? Is equal to mc over I, right? Okay. And actually, it should have sigma xy also. Sigma xy, okay? If it's at midspan, you see that. If we're talking about the shear stress at midspan, the shear force diagram is what? It's 0, right? V equal to 0. But at midspan, bending moment is maximum. Okay? So the shear stress, that is, you know that the shear stress for beam is what? VQ over IB, right? But if we consider at the midspan, the shear force is 0. So tau xy is equal to 0 also, right? And if we consider at this point, you see that for the outplane or the side surface of the beam, we mentioned that it has no load, right? So sigma cc is 0, right? Okay. And for sigma yy also, okay, if we mention just only two-dimensional, okay, we will not talking about the pressure. If we talking about the three-dimensional, okay, sigma yy, it has the load also. But if we focus on just two-dimensional problem, sigma yy is become 0. So according to this, so when we write it in plane problem, it will have just only sigma x, that is equal to mc over I. Okay. And when we write the stress tensor, if we write it in three-dimensional, so that means we have mc over I over here. Okay. But another component is 0. If we reduce to two-dimensional problem, that is talking about just only xy plane, the stress tensor for two-dimensional, it may be reduced to just only this. That's represented by just only xy plane. This is a state of stress at this point. Okay. But if we not focus on this, we may move to this. If we move to this point, what happened? Move to this point. So we have the moment also, and we have shear also. So what does it mean? It means that we should have both normal stress sigma x equal to mc over I, and we should have shear stress also. That is sigma xy equal to what? It should be vq over ib. Okay. So this is the state of stress of this point. Okay. For the state of stress at this point, you see that you have the normal stress along the plane x, along the plane x is not the principal stress, because this plane you have shear stress also. So sigma x that is equal to mcoi of this at this point is not the principal stress, because it had a shear stress. If we would like to find the principal stress, principal stress is what? Principal stress is the normal stress on the plane that has no shear stress. So what does it mean? If we consider this point, so sigma x equal to mcoi of this case, of this point over here. This is a normal stress, sigma x is a normal stress on the plane x that the shear stress is equal to 0. So this is the principal stress. Okay, but if we come back to this, so we consider plane y, right? We consider plane y. For this, sigma yy, this is a uniaxial load test. Okay, sigma yy is normal stress, and on this plane, the shear stress is equal to 0. So this is the principal stress. Okay, this is principal stress. And then, if we focus on this point, okay, so what happened? We write the state of stress of this point. The state of stress become what? It's become mc over I, right? And vq over ib. Okay, and vq over ib and mc over I. So you see that this normal stress is on the plane that shear stress is not equal to 0. So this is not principal stress. Okay. In order to find the principal stress, you have to use the stress transformation, right? In order to find the principal stress, you have to use the stress transformation. For the stress transformation, you have learned it before, okay, in mechanics of material. So you may find the principal stress by use the Mohr circle like this. You may use Mohr circle. That is what? The principal stress, the formula is maybe easy to remember, sigma max, sigma min. Because the principal stress is at over here, so you see that it is the maximum and minimum of the normal stress. Sigma max is and sigma min actually is easy to understand. It is the average, sigma average, plus the radius of Mohr circle, plus or minus radius of Mohr circle. Sigma average is what? Is sigma x plus sigma y divided by 2. Okay, the radius of Mohr circle is what? The radius of Mohr circle. Radius of Mohr circle is determined from Pythagoras. If you understand the Mohr circle, this point, this length, actually, this may be sigma x, it should be sigma y. So this length, it should be sigma x minus sigma y divided by 2. Okay, this is tau xy. So what is it? The radius is easy to remember. This is the square root of, from Pythagoras, the difference in x and y divided by 2 square plus tau xy square. This is the radius of Mohr circle. So the principal stress can be easy to determine by using this formula. The average stress plus or minus the radius of Mohr circle. Okay, so I hope that you may understand the thing that I have reviewed you or overview you in the topic of theory of elasticity. And next time we will focus on the theory of elasticity. Okay, and I hope that you may come back and review a little bit on the mechanics of material. That's actually I include some example to you as you may review it before. Okay, I know that this topic is maybe tough because it is a lot of mathematics and it is in depth of mechanics, So it should be enough for today. Do you have any question?